There are a few theories for bagging which are all similar, and the basic claim is that the error of a bagged output is always smaller than that of a typical individual model. Now, in order to explain this claim, I have to define some assumptions and get a bit more specific. So let's now look at some details of the theoretical argument. We have k models. Each model has an individual output y hat k, and the bagged output is the average over those. And the individual output is some sigmoidal version of the summed inputs. Now I work on a classification task, so target of pattern mu is 1 or 0. The actual output for this pattern mu of the variant k of my perceptron is y hat k. And so this will depend on the activation of this pattern and the target. So let's look what this variable a means. It's sort of something like the distance from the threshold. If this is my gain function, then for negative examples, the error is like this. I have a target 0. I subtract something positive on that side, so it goes down here. And even that one, which is close to the threshold, has a slight negative mismatch. Delta is negative. Now for positive examples, I have a function like this. T is positive. Once I'm very well on the positive side, the mismatch is 0. And then I have here this smooth transition of the mismatch delta. So delta is the signed mismatch between the actual output and my target value. So let's now repeat this. Here again, the transition function. This was the delta. I call this the signed mismatch in the output. And this is our formula. And then the total error in the output would be the sum over all p patterns of this signed mismatch squared. So this is a mismatch. It can be positive and negative. This is squared. It's always a positive error. So let's look at the claim again. A bagged output has smaller quadratic error than a typical individual model. So the output of copy k is transformed into this signed mismatch, and then this is the error of an individual copy. Let's now do the same kind of thing for the bagged outputs. The bagged output is just the average over all these outputs. The signed mismatch is now the bagged signed mismatch, and the total error in the bagged output is the sum over all the mismatches squared for all the patterns. So we are now in a position to give a more precise definition of the claim. We assume that the average delta difference, the signed mismatch, defined as the average over all patterns of this delta k mu, is the same distance d for all copies of the model. Then the claim is the typical error in an individual model, and so this is the error in model k, and this is the averaging sign that says be average over the models. Then this typical error is larger than the bagged output error, defined as the delta difference squared of the bagged output. So this is the claim. Now let's start the proof. We already introduced this signed mismatch, the delta difference, and we talked about the assumption that the average delta difference is the same for all copies, and we will exploit that. Now we shift everything to mean 0. So we define epsilon k mu is delta k mu minus this average delta difference, and then the mean of this is now 0, trivially 0. We can also look at the variance. The variance is this epsilon k mu squared and averaged over all patterns. Well, this is what I call V, the variance V. So now let's look at this average error of a typical model. It's this averaging sign means 1 over k sum over k, and this is just our error. And now we can rewrite this. Since epsilon is delta minus d, then delta is epsilon plus d. We square this. And now we can multiply this out. And what we get here is exactly this variance term and then a d squared term. And the mixed term epsilon times d, they all disappear because this is 0. So here's again the result that we just derived. The typical error of a single copy is this. Now let's look at the quadratic error of the backed output, and then we compare the two. For the backed output, well, we just use the delta of the back. What is this delta of the back? Well, it's based on the backed output, and we do the same kind of shift. We shift to mean 0. We introduce these epsilons, and then the backed epsilon automatically, when averaged of the patterns, also has a 0, which it inherits from the definition of the individual k copies. So let's now work on this. We plug in delta equals epsilon plus d. Now we multiply it out. We have a d squared, and then we have a 1 over k times v. And the 1 over k comes from the fact that this is already averaged here. And what happens is that if you multiply this out, we have lots of terms where we have sum over k, epsilon k mu, sum over m, epsilon m mu. These are the mixed terms, and the term over here is the diagonal term where k is equal to m. And now, if the data is uncorrelated for different copies, so if copy k of our instantiation of a perceptron, say, sees something different than the copy m, then this is uncorrelated. If this term is uncorrelated, then in fact it goes to 0. And that means we have, if you compare this one with this one, that we have two terms. D square is the same on both sides, but here we have a v, and at the lower part we have a v, but at this part here we have a v, a variance divided by k. So if we increase the number of copies, this goes down. Now note that this requires indeed that this term vanishes. If there are remaining correlations, then the results will become a bit more similar. So let me summarize what we have seen. We have made the assumption that the average delta difference is the same for all k copies. And then we showed that the backed output has a smaller quadratic error than a typical individual model, which means averaged over the model. And if all individual models are uncorrelated, which basically means they use uncorrelated data, then the gain in performance scales as 1 over k. You remember this variance term scales with 1 over k. Thus, a backed output is always better than an individual network. Now, let me make a couple of remarks. So the assumption was a statement on the average delta difference. Well, important is to note that the assumption is not for the quadratic error. It's really for the signed mismatch, which can be positive and negative. Well, it's sort of natural. I tried to explain it with a picture at the beginning. If due to learning, at the end of learning, the separating hyperplane has found a good position, then you would expect that, well, there are a few positive examples, some negative examples, they will cancel out, there might be a small difference, and why should it be different between one model and the next? So with a good error function, D might even vanish. Now, to get this increase, where the variance disappears with 1 over k, it's really necessary to have uncorrelated data. Well, if you think about it, they would be really different, the different copies, if each of them had a completely independent data set. And then it's kind of obvious, because that means I have much more data. And if I have more data, I can be better. Now, we don't have more data, but this resampling is quite a good trick to construct data sets that are somewhat independent. Final remark, our theorem is on the backed output. It does not include the majority vote at the end. So I presented a specific variant of a bagging theorem, but of course there are other variants out there in the literature.